Okay then, it's your last one with me for a little while, and it's as hard as electric circuits are gonna get. It is potential dividers. So before you really dive into this video, I want you to just take a little moment to think for yourself. I would like you to have a little look at the circuit and just have a think, how would changing the size of resistor 2 affect the potential difference across resistor 1? And then I want to see if you have any equations that you can use to back up what you're saying. So think about it qualitatively first. If I make resistor 2 bigger, what will happen to the potential difference across resistor 1? If I make it smaller, what will happen? Then, once you've thought about it qualitatively, go find some equations and see what you can do. So once you've done that and you've had a little play, then come back. But really do have a little think, check that you can work your way through this sort of problem. If you end up with anywhere near the answer that I'm going to get to, you should be really pleased and know that you get electric circuits. And if not, don't worry, you will never have to derive this in the exam. But give it a shot anyway. So, basically, we're saying I've got a circuit that looks like this. I've got resistor 1 and resistor 2, and I have voltage 1 across resistor 1 and voltage 2 across resistor 2, and I've got a potential difference, a terminal potential difference going into my circuit. So my, in essence, EMF, because we're going to ignore internal resistance. And that is a potential divider circuit, because what it's doing is by having two fixed resistors, I'm splitting my potential. I'm dividing my potential between these two components, so it gives me a fixed source of potential difference. And they're really useful, these, because I can use them to control the amount of output I get. I can make sure that I get the right volume. If I change the size of one of these, I can make my output louder or quieter, so volume control. Automatic light control, if it works with these thermostats, is another one. So these are really useful circuits, these potential dividers, so you do want to get your head around them. But that's all it is. It's a circuit with multiple resistors in it. So let's go to the theory, the thing I asked you to have a little think about for yourself. Back to my circuit, bog standard, super duper simple. If I have a look at the current that's flowing through it, so if I just consider the current, I could say that it's equal to my total EMF divided by my total resistance, which in this case is R1 plus R2. So I have that V1 is equal to I times R1. So if I substitute that equation for I into what I've got going on here, this into here, I can see that V1 is equal to V0 times R1 over R1 plus R2. Is everyone happy with that? All I've done is that I've taken this equation for I and I've plopped it into here. I could do the same for V2. I can say that V2 equals I R2, and if I plop in this equation, this term for I, gives me that V2 equals V0 times R2 over R1 plus R2. So if I take these two equations and divide them by each other, I can see that the ratio of the voltages across my two resistors is equal to the ratio of the resistances across them. Hopefully you should actually already have known that, because we've kind of been teasing that out as we go along. All I'm saying is that potential differences across my potential divider are in the same ratio as the resistances. So it's pretty straightforward and simple. Now when you're working this out in the exam, they prefer you to use this equation here, and this version here. So either way, it doesn't matter. V1 equals, or V out equals V in over R1 plus over R. Let's try that all again. V out equals V in over R1 times R1 over R1 plus R2. There's something wrong with me. Anyway, this equation here, this one, and that's what they want you to use. You can use this as your check and as your sort of like your mental reminder, have I done it right? Does it make sense? But it's based in these equations here. So let's consider, if I wanted to have a variable potential difference, how could I achieve it? Well, really simply, I could just have a power supply and then a length of wire and then a contact. So if I put the thing I'm interested in across this contact here, and I can slide this along the length of the wire, well, when I slide it, if it's bang in the middle, I'd get half. If it's a quarter of the way up, I'll get a quarter. If it's 3/4 of the way up, I'll get 3/4. And I can get anything in the range from all of it to none of it. And that's how the potential divider works. Length of wire, just slide it up and down. And that comes from the idea that of resistivity. So we know that the resistance is proportional to the length, so I can just change the length to change the resistance. Another way, if I want to try and save a little bit of space, is I can coil my wire around something and then my contact just moves around the coils. Now I won't get quite the same range I will with the wire because it's just going to go from one loop to another, but it still gives me a very big range and takes up less space. It's kind of what you can imagine, or what is inside a volume dial. So when you twist it, that's what you're moving around. And this is the symbol for a potential divider circuit. So this is a resistor, and then we show that we've got a flying contact. That's what this arrow means, a flying contact, one that you can move up or down. And in this case, the thing I was interested in powering would probably be here, so that I can change how much voltage it gets by changing the ratio of the resistances. So output is by connecting from C and B, and this output would be a maximum when the slider is at A, and a minimum, normally 0, when the slider is in position B. So the great advantage of potential divider circuits is they give me the widest possible range of values. Because I can go from 0, I can get some really tiny voltages out much more easily than if I was using fixed resistors. I can go right the way down to the bottom. And I can also get essentially the full EMF from the power supply out as well. So they're very good for investigating things where I want to change currents, particularly if I'm interested in small currents. So another example of the use of a potential divider circuit is like this one here, is to control the brightness of bulbs. So as the slider of the potential divider is moved up, the bulb brightens up from nothing to its maximum. And it means I have a full range, it's continuous, the range of settings for the light bulb, I don't have to go for set things. The downside is I might possibly still have a glow even when I'm at the maximum resistance, so I might not be able to turn it all the way off. I can use the same system for a speaker as well. That's the bog standard simple one. I'm glossing over it because it's pretty easy. The more interesting one is where I have a thermistor or a LDR in there. So I have so essentially a thermocouple, so something whose resistance changes depending on the environment that it's in. So if you look at this circuit here, I've got a variable resistor and I've got a thermistor which I've attached to a, in this case, just a voltmeter. But I could put a heater here, and that would give me a very useful circuit. So let's have a little think about what's going on here. So at constant temperature, the source potential difference, so the source, the terminal PD from this power supply, is split between my variable resistor and my thermistor. The output of the circuit is what goes across my thermistor, so the thing I'm interested in, which is why I put the voltmeter there. And I could stick a heater in there if I wanted to, as I said. And the reason I might want to stick a heater in there is because when the temperature goes down, the resistance of the thermistor will go up. So the power going to the thermistor and the heater, if I put it where the voltmeter is, will also go up. So in other words, when it gets cold, the heater will turn on. And equally, when the temperature goes back up, the resistance in the thermistor will go down, because it has a negative temperature coefficient. It will go the opposite way to the temperature. So temperature goes up, resistance goes down, heater turns off. It's really useful, really helpful. It's kind of how the heating system in your house works. So why do I want a variable resistor in here rather than a fixed resistor? Well, as they love to do in exam questions, it is because by changing the value on the variable resistor, I'm essentially changing the point at which the heater will come on. So it's like changing the temperature on your thermostat. You are just changing the resistance that's in your potential divider. And it's pretty simple and straightforward. I can do exactly the same thing if I want to have a light that turns on when it gets dark. So I have an LDR this time, again with my variable resistor, and my output would be here, and in most cases that would be a light. So constant level illumination, it's split between the two. The output of the circuit is what goes across the LDR, light level goes down, resistance in the LDR goes up, so voltage goes up, so the lamp turns on. Now obviously, if you were setting up the circuit and you had a lamp here, you would obviously need to put some sort of division or barrier between your lamp and your sensor. Because otherwise, if it got dark, the light would go down, so the resistance in the LDR would go up, so the voltage would go up across the branch, so the light would turn on. Once the light came on, the light would go up, so the resistance on your LDR would go down, because the light's shining on it. So in that case, the voltage goes down, so that means that the light turns off. But then it got dark, and basically your light would just flash on and off, on and off, on and off. So you always want to make sure that your light, your LDR, is not in the line of sight of your light. So basically, if you think of street lights, the sensor goes on top of the light and the light shines down. So sensor, light pointing down, so it works, it doesn't turn itself off and on. Another real-world application of your physics. How nice, hey? And that is it. We are done with all the electric circuit stuff now. We're just going to look at some applications of it and just how mean the exam board can get with it. But it's not actually too bad, really. And next up you'll have capacitors with Liam, which will be the last little bit of electric circuits. So it should be pretty straightforward for you. I hope this hasn't been too boring, because I know it's a lot easier than what we've done so far. But enjoy it whilst it lasted. Or I hope you enjoyed it whilst it lasted. Sorry. So remember, any questions, just ask when you see me on Liam.